In this session, we discuss two concepts: speed of a particle moving along a curve given by a vector valued function and the unit tangent vector to the curve at each point corresponding to the parameter t. We recall the definition discussed in the previous session. The length of a smooth curve given by the vector valued function r of t is equal to x of ti plus y of tj plus z of tk, that is traced exactly once as t increases from t is equal to a to t is equal to b, is given by the definite integral L is equal to integral from a to b of square root of dx by dt square plus dy by dt square plus dz by dt square dt. Since the velocity vector v of t is equal to dr by dt, the above formula can be written in the arc length formula in the short form as L is equal to integral a to b absolute value of v of t dt. In the previous session, we have also seen that if we choose a base point p of t naught on a smooth curve c parameterized by t, then the directed distance measured along c from the base point p of t naught to the point on the curve corresponding to the parameter t is given by s of t is equal to integral t naught to t square root of x prime of tau square plus y prime of tau square plus z prime of tau square d tau, which is equal to integral from t naught to t absolute value of v of tau d tau. In order to discuss the speed on a smooth curve, we note that s of t is a differentiable function of t. Also, the derivatives beneath the radical are continuous, so the curve is smooth. Then, the fundamental theorem of calculus tells us that s is a differentiable function of t with derivative ds by dt is equal to absolute value of v of t. As we expect, the speed with which the particle moves along its path is the magnitude of v, as we observed in the above equation ds by dt is equal to absolute value of v of t. Notice that while the base point p of t naught plays a role in defining the arc length parameter, s of t is equal to integral t naught to t square root of x prime of tau square plus y prime of tau square plus z prime of tau square is equal to d tau, which also is equal to integral t naught to t absolute value of v of tau d tau. The base point plays no role in defining ds by dt is equal to absolute value of v of t. The rate at which a moving particle covers distance along its path has nothing to do with how far away the base point is. In real life also we have this feeling, because the speed of a moving particle in general does not depend on the point from where we start the journey. Notice also that ds by dt greater than 0, since by definition absolute value of v of t is never 0 for a smooth curve. We see once again that s is an increasing function of t. The arc length parameter function s is an increasing function of t. That is to be noted. Now we discuss the unit tangent vector t. Since ds by dt strictly greater than 0, for the curves we are considering, s is a one-to-one function and hence it has an inverse that gives t as a differentiable function of s. Then the derivative of the inverse is given by dt by ds is equal to 1 upon ds by dt is equal to 1 upon absolute value of v. I suggest the students to go through your preliminary calculus books to get this formula. There you have seen that if f is a differentiable function that has an inverse, there is a formula to express the derivative of f inverse in terms of f. This expression dt by ds is equal to 1 upon absolute value of v makes the vector valued function r a differentiable function of s whose derivative can be calculated with the chain rule, and it is dr by ds is equal to dr by dt times dt by ds, which is equal to v times 1 upon absolute value of v, which is equal to v by absolute value of v. Here note that v is a vector valued function and absolute value of v is a scalar. And after finding the absolute value, it becomes a scalar function. The above equation says that dr by ds is the scalar 1 upon absolute value v multiple of the vector valued function v. So dr by ds is the unit tangent vector in the direction of v. We call dr by ds the unit tangent vector of the curve traced by r and denoted by t. Definition: the unit tangent vector of a differentiable curve r of t is equal to dr by ds is equal to dr by dt by ds by dt is equal to v by absolute value of v. The unit tangent vector t is a differentiable function of t whenever v is a differentiable function of t. We can also write the above equation in the form t of t is equal to v of t by absolute value of v of t. See, here you note the point that in terms of the arc length parameter s, the derivative dr by ds simply gives the unit tangent vector. At the same time, if we use the parameter t directly, in order to get the unit tangent vector, what we have to do is we have to find v of t by absolute value of v of t, which is nothing but dr by dt all divided by absolute value of dr by dt. That means in terms of the parameter t, unit tangent vector t of t is dr by dt all divided by absolute value of dr by dt, and at the same time in terms of the arc length parameter s, it is simply dr by ds. We will see in later sessions that the unit tangent vector t is one of the three vectors in a traveling reference frame that is used to describe the motion of space vehicles and other bodies moving in 3 dimensions. Now we find the unit tangent vector of the helix r of t is equal to cos ti plus sin tj plus tk at the point t and also at the point t is equal to pi by 2. Here the velocity vector v is equal to dr by dt is equal to the derivative of the vector valued function r of t, and it is negative sin ti plus cos tj plus k. So its absolute value is square root of negative sin t square plus cos t square plus 1 square, which gives square root of 2, because we know that sin square t plus cos square t is equal to 1. So the unit tangent vector of the helix at the point corresponding to the parameter t is the vector t of t is equal to t, which is equal to v by absolute value of v, which we write as negative sin t by root 2y plus cos t by root 2j plus 1 upon root 2k. At the point corresponding to t is equal to pi by 2, t of pi by 2 is equal to negative sin pi by 2 by root 2i plus cos pi by 2 by root 2j plus 1 by root 2k, which simplifies to the vector negative 1 by root 2i plus 1 by root 2k. As another example, we find the unit tangent vector to the curve given by the parameterization x is equal to t square plus 1, y is equal to 4t minus 3, z is equal to 2t square minus 6t at the point t is equal to 2. The position vector of a point on the curve is given by r of t is equal to x of ti plus y of tj plus z of tk, which is equal to t square plus 1i plus 4t minus 3j plus 2t square minus 6tk. So velocity vector v of t is equal to dr by dt is equal to 2ti plus 4j plus 4t minus 6k. Then absolute value of v is equal to absolute value of v of t is equal to square root of 2t whole square plus 4 square plus 40 minus 6 whole square, which simplifies to the scalar valued function 2 times square root of 5t square minus 12t plus 30. So the unit tangent vector at the point t is the vector t is equal to t of t is equal to v by absolute value of v is equal to 2ti plus 4j plus 4t minus 6k all divided by 2 times square root of 5t square minus 12t plus 13, which is equal to ti plus 2j plus 2t minus 3k by square root of 5t square minus 12t plus 13. Therefore, at t is equal to 2, the unit tangent vector is the vector t given by t of 2 is equal to 2i plus 2j plus k by 3. For the counterclockwise motion, r of t is equal to cos ti plus sin tj around the unit circle. The velocity vector v is equal to dr by dt is equal to negative sin ti plus cos tj. And this is already a unit vector since absolute value of v is equal to square root of negative sin t whole square plus cos t square is equal to 1. So the unit tangent vector is v by absolute value of v is equal to the vector v. So at each point on the unit circle corresponding to the parameter t, the unit tangent vector is the same as the velocity vector there. What happens when we consider a circle of radius a instead of considering the unit circle? Okay, now consider an example. We find the unit tangent vector at the point t to the circle of radius a having the parameterization r is equal to a cos ti plus a sin tj in the same anti-clockwise direction. See, here also we consider a parameterization that gives a parameterization for the circle in the counterclockwise direction. Here the radius of the circle is a. Now we find the velocity vector v of t and it is dr by dt that is equal to negative a sin ti plus a cos tj. So the unit tangent vector is given by t is equal to v by absolute value of v is equal to negative a sin ti plus a cos tj all divided by square root of negative a sin t whole square plus a cos t whole square, which on simplification gives negative sin ti plus cos tj. Now we conclude the session by considering an example by finding the unit tangent vector of the curve given by the vector valued function r of t is equal to cos t plus t sin t I plus sin t minus t cos t j where t greater than 0. Here the velocity vector v is equal to dr by dt and which on simplification can be seen that is equal to t cos ti plus t sin t j. Absolute value of v is equal to square root of t square cos square t plus t square sin square t, which is equal to square root of t square is equal to absolute value of t is equal to t, since absolute value of t is equal to t when t greater than 0. So the unit tangent vector at the point corresponding to the parameter t is equal to v by absolute value of v which is equal to v by t, which is equal to cos ti plus sin tg. Thank you. We will meet again.